Okay, so let's start. Last time we were talking about, we saw three applications, right? One was electric vehicles, the other one was solar photovoltaics, the third one was mobile phones, right? All three applications we saw there is a lot of power electronics, and we just took these three applications, but in reality you can take any other electrical appliance or any other electrical equipment around you, and you will see there is a power electronics in it, right? And then we saw that, for example, DC to DC converter and AC to DC converter, these were the two common converters which were used in these applications. So we just looked at, let's say, DC to DC converter, and we are exploring what are the possible ways to do this conversion, right? So the simplest way, based on what we learned so far in previous classes, we thought that, we just couple a motor and a generator, and that would sort of take care of the DC to DC conversion process, right? You can have a DC-DC, you can have a DC motor and a DC generator. You can either design them differently with different pole pairs, or you can have a gearbox so as to get different input and output voltages, right? But this one has, of course, a very big size, right? Cost would also be high. So then the next possibility was just use a small resistance divider. If you have to do buck, if you have to boost, then maybe this will not work. But if you have to do buck, you can use a simple resistance divider. So for example, from the 5 volt supply which comes to the phone, and then the 3.3 volt which goes to the battery, right? From 5 to 3.3, you could have probably done a buck using a resistance divider. But we saw that this is not a good way because efficiency would be poor. There is always losses happening in the shunt 10K branch, right? In addition to that, if the load changes, then the output voltage will also change because the load resistance is coming in parallel to the 10 kilo ohm resistance, right, in this screen. So these were the two problems. So then we looked at linear regulators, which are essentially in a way controllable current source or controllable resistances, right? And you can see if I use a MOSFET or even a transistor for that matter, then controlling the gate to source voltage or the current, if it is a BJT, I can control the drain current, right, or the channel current. And if I suitably choose a channel current based on the load resistance, then I can maintain the voltage. So the problem of load voltage variation because of load resistance change can be taken care of by using a variable resistance, and of course some other circuit which can monitor the output voltage, which can do the subtraction, we can figure out whether the output voltage is less or more, right? You have done some basic course in control systems so far? Have you done any basic course in control systems? It's going on now. What is the course? Control systems. Okay, so you would see, right, this is basically a simple control system where you have something to observe, and then you want to track that output voltage to a specific value, and it's like a basic control systems. The problem still with this guy is, yes, we have avoided the shunt resistance more or less. We can keep a very large value of shunt resistance only for light load case, but still there is a voltage drop, right? So if I am generating 50 volt to hypothetically 25 volt, which is the case with this thing, let's say I am doing, right, so if you are doing 50 volt and let's say output voltage you want is 25 volt, right, and your output current is 2 ampere, right, then the output power in this case is 25 into 2, which is 50 watt, right, but the input power, or rather the power loss happening in the devices, because the voltage drop across the series device is 50 minus 25, so the power loss that is happening is input voltage minus output voltage, and the same current whatever is flowing from the load, right, because assuming the other resistance is very, very large, the same current is practically almost flowing through this series device, right. So 50 minus 25 into 2 ampere, so this comes out to be another 50 watt, right. So to deliver 50 watt, you have almost 50 watt of losses, right. So efficiency is 50%, which is not that great, better than the previous one, but still not that great. Yeah. Oh, shunt was there. Anyone remembers why there was a shunt? Yeah. Okay. Iffy. Correct. So if you completely remove the load or the load becomes very negligible, right? Your system may no longer be controllable system basically, right? Because output you may have some sensitivities, right? How much gate voltage you can change. If you change it slightly, suddenly output voltage will jump. There is no way to reduce the output voltage. There is only one way control. If you have a load resistance, then you can increase the gate, voltage will go up because current will go up. If you reduce it, assuming there is small parasitic cap at the output, right? Just imagine there is a small cap, just parasitic. There is no way to discharge it. If there's always a load, you have both the options. You can increase the output voltage by pushing more current. If you reduce the current, the voltage will come down. But if there is no load, then that option sort of goes away. So you always keep minimum resistance, a very large value of resistance connected, which does not really create lot of losses. V square by R, so R is, let's say, in tens of kilo ohms, so it will not create so much of loss, but then it does help you in maintaining the output voltage, right? Okay, so this is something which you have discussed in 113. I think we should not talk about it now again, right? So by no load, we mean there is no current, right? Which implies that the resistance is infinite, right? By light load, we means small current, implied resistance is very large. By heavy load, we imply large current, means the resistance is small. So we always, load means basically we are talking about load power or load current, right? Not the resistance, right? This is something which, at least for this course and for all the power related courses, this is the terminology very commonly used. Okay, so now there is, things are looking good, but then still not the best solution. So we looked at another solution, which is the switching regulators, right? Where, which is so far seems to be the best solution, where you use two switches. Let's assume these are ideal switches, and you close one switch. Your supply voltage is 50 volt. You get an V alpha, which is equal to 50 volt. You close switch 2, open switch 1. You get V alpha is equal to 0, right? And if you keep doing that on and off, on and off, on and off of the alternate switches, then you get this trail of pulses at V alpha, which is 50 volt 0, 50 volt 0, 50 volt 0. Let's say you are doing it very, very fast, right? And I gave you the example of what if you look at an incandescent bulb. Actually, in incandescent bulb, it's glowing and then going off, glowing and then going off, but then we perceive it as a continuous light, right? Because our eyes in a way cannot capture that high frequency phenomena, or they act as a low pass filter. So similarly, if this high frequency trail of pulses passes through a low pass filter, if you see the contribution in this pulses, there is a DC component, which is the average component, plus there is a high frequency component, right? So if you do a low pass filter, it stops the high frequency component, it only allows the DC component to pass through. So if you pass this trail of pulses through, let's say, an inductor and a capacitor based low pass filter, then what you will get at V beta is almost pure DC or maybe very small ripple, right? Not as large ripple as what was there in V alpha, because majority of the high frequency will be blocked by this low pass filter. We will do more about this filter, we will do learn more about this switching, but this is, if you see, this is nothing but the buck converter which you might have studied. If you put the filter and the switch together, right, you can imagine this was the buck converter which you may have studied long back in 103, right? But anyways, we will come back to more detailed operation of this circuit. So if you are able to understand at high level now, I think that's okay. We'll relook at it. This is how most of the power electronic converters operate, right? We don't want to do linear regulators. We don't want to create a lot of losses. The objective is that you have a low frequency, the 50 hertz or a DC voltage. You overlap it with a very high frequency component, right? And then you filter it out, right? And in the process, change the voltage levels or the magnitude or the frequency, whatever you want to do, right? But that's the basic principle. As we move forward, I'll give you more examples. So this sort of concept becomes more clear to you. For this, what you require is a switch, right? S1, S2, and an inductor and a capacitor. Right now, inductors and capacitors, by now, I mean, we have been talking about it from quite some time, and you know these guys exist and you have seen them. The switch S1 and S2 we are talking about cannot be a mechanical switch, because if it's a mechanical switch, it will take its finite time to close and open, right? Which could be, let's say, anything between a few seconds in best case maybe it can maybe do in half a second or something like that, right? But you cannot talk about switching at kilohertz, right? That means 1000 times switching in a second, right? You cannot talk about switching 100 kilohertz, that means 100k times on and off happening in 1 second. You don't expect that with a mechanical switch, right? So this switch is very important for power electronics, and this could be, for example, your MOSFET, right? So this could be a MOSFET. How we use MOSFET? If you have to use it in this circuit, you can turn it on, right? So that way your gate voltage is 6 volt. You are in this topmost characteristics, right? Your drain to source. This is x-axis is drain to source voltage, y-axis is drain current, right? You have seen this graph before. You have learned about MOSFETs. Okay. So if I give gate to source voltage 6 volt, then I am on the topmost graph, right? So I can actually push 25 ampere of current through this switch by creating just a small drop of about 2 volts, right? In this state, I would call it as a on state. If I give the gate to source voltage 0, right, then it can actually block very large voltage and will not allow any current to flow, right? So this is like switch is open, right? Because when switch is open, it will not allow any current to flow. When switch is closed, it can allow any current to flow with a very small drop created across the switch, right? So you can see this point, I can call it as an off condition. So now if I can, when I want to close the switch, I can give gate to source 6 volt. It will be acting as a short circuit, not perfect short circuit, but a very, very good short circuit, because your voltage drop is only 2 volt, even if you are pushing very large current of 25 ampere. And when you want to open it, you give a gate to source voltage of 0 volt, and this would not allow any current to flow, even if you apply 14 volt, even if you apply 100 volt, whatever, right? So this sort of feels like a switch, right? Feels like a switch which you could have used in the previous circuit. Plus, because it's semiconductor switch, it can switch much faster, right? It can switch in kilohertz, there's no problem. If you remember the previous circuit where we were talking about linear regulators, right? And this was a question some of you asked. At that time, we were operating somewhere in this region, shown by the bigger circle, right? Because the switch was acting as a current source, and we were operating in this saturation region, so to say, right? Now we are operating it either in the ohmic region or in the off region, right? So that's also another difference when we are talking about this power electronics or the switching regulators. It's the same device more or less, but the point at which we are operating is different. Now we are operating them either at cutoff region or in ohmic region. That means the switch is on or switch is off. There's nothing in between. But when we want to use it as a linear regulator, then we want to operate them in between, because we want them to mimic a resistance or a current source, right? So they are neither completely on, neither completely off. They will have a large voltage drop, and they will also allow current to flow through simultaneously. Okay, any doubts? Yeah, sure, of course. It's just an example. Yeah, so depending on, so his question is that would you always have 25 ampere? No, I mean maybe you have 20 ampere, then your voltage drop will be different. Maybe if you know your load current is 100 ampere, you won't use this MOSFET. You will buy another MOSFET which will have the characteristics so that even at 100 ampere you will remain in the ohmic region. You will use that MOSFET, not this MOSFET. Right? So depending on your requirement, you have to choose the MOSFET. Of course, I mean, yeah, I mean that's true. So universally, you cannot just build one mobile phone and ask everyone to use the same phone, right? You want something else, he wants something else, I want to use something else, right? So that's always true, right? There are so many cars. It's not like only one car and then everybody go and buy that car. Yeah, ideally that would have been, if you can do that, that would be fantastic. But that's not how things would work, right? It would be an overkill also. For example, yes, I can make a phone which everybody would like, but that'll be so expensive. Nobody will end up buying it, right? Because it'll have features you want, he want, me, I want. So that doesn't make sense, right? So there are so many MOSFETs. So if you go back and if you Google, right, for example, there are some online stores where you can buy the MOSFETs, for example, right? There's something called as RS component, Mauser Electronics. So many of them are there. You go there, you search MOSFET, you will get hundreds, thousands of these devices with different current rating, different voltage ratings, basically, right? Okay. So switch, as we call it, is one of the most important thing in power electronics. There are different names, and I might use these different names as we go through the course, and also you would see that different books, other professors might use some other names, right? Somebody would just call it a power switch, somebody would call it a power semiconductor device, somebody would call it a semiconductor switch, somebody would call it a controllable switch, somebody would call it just a switch, right? So all of these things in our mind, you should be able to map it to the application we just saw, right? Okay, let's start with a little bit of history. I know you might have learned history in some of the other courses as well, especially in 103 maybe there was a little bit of history component. But let's look at a little bit more from the power devices perspective, right, how it evolved. So most of the semiconductors started happening in 40s, 50s, yeah? 1940s, 1950s, 1960s, when Fairchild got found. You might have heard of name called William Shockley, who was one of the inventors of BJT and a lot of these things, right? But 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 then before that, there was still something with which people were able to do AC to DC conversion and so on, right? So just to sort of fix timelines with you, don't, I mean, at least for this course, we don't need to remember anything before 18, let's say 1880s or something, right? You remember Faraday's disc? There was this simple disc, I might have showed you the picture, right, which was like a DC motor, very simple DC motor. Maybe you don't remember, go back and Google. That was, I think, in mid 1800s. Towards the end of 1800s, there was AC, there was DC system. People were fighting that which one is more prominent. Then from 1900s to 1950s, right, there were some other kind of devices being used, which is this mercury arc wall. And 1950 onwards, semiconductor really picked up, and now of course we use a lot of semiconductors, right? So before semiconductor, in 1900, 1902, there was something invented which was called as a mercury arc wall, or also known as just mercury arc rectifier, by Peter Cooper Hewitt in US, right? And this was a glass bulb based arc wall. So the enclosure was made up of the device had an enclosure which was a glass bulb kind of shape, and then later on some steel version of it was invented because glass was fragile. If you transport it will break, so people said, okay, let's not use glass, let's use steel. And so many other innovations happened in the next 10, 15, 20 years, right? A lot of them, which we'll not go in details of. But the basic device was very interesting, and you remember this is before MOSFETs, right? You don't know what is MOSFET, you don't know what is BJT, you don't know any of those things, right? And this is a device which is almost a switch, almost a switch. So if you see, this is the structure. This is the, it looks like a bulb, it's made up of glass, right? So this is the structure. This is cathode pool of liquid mercury, right? So there is liquid mercury which is floating there. Okay, and then this is anode made up of carbon, graphite carbon basically, right? And this is completely sealed, this bulb is completely sealed. So this mercury liquid is there, but there is also mercury vapors in and around this chamber. Okay, now mercury emits lot of electrons, right, which can easily go from this pool of mercury through this air vapor of mercury, and then it can be absorbed by carbon or graphite sitting here, right. So what it did, it can allow the current to flow through. If the electrons can flow through from mercury from the bottom to the top, then the current can flow from top to the bottom in a way, right. So it allowed current to flow in this direction only, right, didn't allow current to flow in other direction, because the electrons would only go from mercury to the carbon, right. And this, you can imagine what kind of device this sounds like. Have you seen any other device very similar to this? Diodes, right? It's like a primitive diode, if you want to call it. So these guys are anode, right? This is anode, you call it anode, and the same nomenclature we use in diodes as well. And this other guy, we call it as cathode, right? So cathode is made up of a liquid mercury anode is graphite or carbon, mercury emits free electrons, and when there's an arc gets formed, then the electrons flow through the ionized mercury vapor to the anode, and that's what makes it behave as a diode. Good point to have to ask questions. Yeah, go ahead. Yeah, there are. I don't have all the answers. So her question is why this shape, why this structure, right? We could have had a simple tube, possibly yes. Difficult to answer now, but I can give you the sense why, for example, this would have happened, right? Maybe this creating this bulb shape, allows the condensation of the vapor which goes back into the molten pool, right? Maybe that is the shape. Maybe that structure allows some water vapor, some mercury vapors to be sort of stored there, so that whenever the arc gets formed, they can quickly come into action instead of new vapors getting generated. I don't know the answer, but what I'm saying is there could be a lot of experimental and physics oriented things which would have gone at that point in deciding the structure, right? Yeah. Okay. Now how it works is that if you just leave it, nothing happens. First thing you have to do is you have to create an arc, right? And for that, an actual graphite or carbon needs to come in contact with this molten pool. First time to create the arc, right? It's like starting the whole system, right? Starting the machine. So you see on the left side, there is something called as a ignition system, right? This one, right? What it does is this part, which is a small rod and which is just slightly above the molten pool, right? You see there's a small gap. So either you tilt this bulb so that these two guys comes in contact, creates a spark and an arc, or you use some sort of a electromagnet here. Whenever you turn button switch, turn it on, this guy will sort of pull down and come in contact, create an arc, right? This was the system. Once it's on, then as soon as you apply a positive voltage here and a negative voltage, the positive voltage the anode, negative at the cathode, the electrons will start flowing, right, if it's on. So yeah, it was pretty complicated system, I would say, but still worked. Yeah, so you use the glass bulb to maintain the low pressure inside, to control the temperatures inside, and to bring the condensed mercury back to the cathode. So we saw that you can start it initially, and then once a system is started, it will keep operating. But then we wanted something more, right? Not just a diode. We wanted something like a controllable switch. That's the objective we have started with. So what was happening is there was this thing called grid control. This grid does not mean the power grid, right? This grid means grid or a mesh, right? So what this grid control did is, which is not there in this picture, is hypothetically you assume that you insert a grid of metal somewhere here, right? And this guy, you provide a negative charge with respect to the cathode. Okay. Now what will happen? The electrons will come out from the molten pool, right? But this grid or this sort of plate with mesh in it has a negative charge, so electrons would not be able to cross those guys, right? They would repel. So they would sort of, although they want to go, they would not be able to go. They'll just get stuck there, right? So now if you have a negative charge on the grid, even if you have a forward biasing of the diode, so to say, this guy will not start, the arc will not create, it will not start operating. So you got some sort of control. Yeah? You want me to repeat this part? Yeah. Yes. So vapors may have some free electrons which would probably try to go there, but majority of the free electrons are still in the pool of mercury, right? So these guys, vapor would help if these guys want to go there, but then because of the negative potential here, they would repel, so they would not be able to cross it. Yeah. So you can control the instant at which you can turn on this device. Even if you have a positive bias voltage, it will not turn on automatically. Similar to BJT, right? For example, BJT, even if you give positive, what are the terminals of BJT? Hmm? Okay, let's talk about a MOSFET, right? MOSFET has gate and drain and source, simple, okay. So even if you give drain to source positive voltage, right, unless you give gate, it doesn't conduct. It's not just a diode basically, it's something more than diode. Same thing you can achieve here, right? Even if you are giving positive voltage from anode to cathode, it will still not conduct unless you remove the negative potential from the grid or you give a positive potential to the grid, right? If you give the positive potential, yeah, then electrons would be very happily jumping around, or you give a zero potential, they'll very happily jumping around and they'll start operation as usual. Is that okay? The challenge is once this arc is formed, right, then a few couple of voltage of negative voltage cannot stop it. That is the problem. So it's not completely like a MOSFET. You can turn it on, but you cannot turn it off. So that's a small catch, right? So grid between anode and cathode, it's closer to the cathode, closer to the molten pool. Negative voltage apply with respect to cathode doesn't allow electrons to flow. Slightly positive voltage will allow the current to start. Arc cannot be stopped by grid control. You can create, you can time the turn on instant, right? But once the current is there, once it's flowing, you cannot control it through the grid voltage. Of course, if naturally if the drain to source voltage becomes 0, then the current will stop. That's fine. But you cannot control it using gate, which you could have in MOSFET, of course, but not here. Right, and that's the reason these kind of devices are called as semi-controlled devices, because they are not completely controllable. You can turn them on, but you cannot turn them off. Turn off will happen based on the drain to source. The gate cannot turn off, right, and therefore these devices are called as semi-controlled. What is the meaning of arc? Arc means the gas will be ionized, right? It would emit a light also, and then it can easily flow current through it basically. I have a picture which shows you that. So this is how it looks like, right, when it is on. Because if there's an arc, it will actually grow, right, and it will emit some light of certain wavelengths. This is the characteristics wavelength of mercury. So you would see this kind of a light coming out of it. This is a picture which I took from internet. This is a restored mercury arc wall which is at Kempton Steam Museum in London, and this was this can take 415 volt, the maximum voltage it can take. A 3-phase rectifier formed using these devices, right? You don't have diodes at that time, so you can form a rectifier using these devices, and the ratings of the device voltage and current is also given to you. These are two, right? Of course. Okay. So the challenge here is, yeah, this one is by the way the glass one, right? I told you about the steam one also. The challenge here is that large size, right? Fragile to transport, glass might break, difficult to transport due to glass vacuum tubes, right? And therefore people started using steel enclosures, and that became more popular, but doesn't look anything fancy, so it's better to look at it than the other one. Any questions so far? Okay. Okay, then let's sort of do a little bit of circuits using diodes, which I'm sure all of you know already, right? So we'll just quickly do it. Some circuits using diode. You know half wave rectifier, full wave rectifier with a resistive load. How many of you have heard of half wave rectifier? Raise your hand. Okay, everyone. So let me draw very fast then. Yeah, so there is an input voltage which is an AC voltage. There's a single diode followed by a resistance, and the question is that if I know and the load is R load in this case, if I know that this is my input voltage, right, how would be my output voltage look like in this case? How would output voltage look like in this case? So if I initially there's zero current, right? Let's say I start from zero, the input voltage is positive, then anode is positive with respect to the ground, but for the diode to conduct, anode must be positive with respect to the cathode. But because there is no current, so anode is positive with respect to cathode as well, because I into R is 0, right? So the diode starts conducting and the current starts flowing in this direction, right? So the output voltage would follow the input voltage as long as the input voltage is positive, right? When the input voltage becomes negative, then anode becomes negative potential with respect to the earth. Again, at zero voltage, almost current is zero, so that there is no motivation or there is no drop across the resistance, and therefore the anode will become negative potential with respect to the cathode, and it will not conduct, so your output will remain 0. Right? This is what the output voltage would look like, right? And all of you are okay with that. Any doubt in this? No doubts. Okay. Then this was half wave rectifier. We call it half wave because at the output you only have half wave. You don't have full wave, right? The other guy is a full wave, full bridge. What is this? Is half wave. This is a full bridge. Right, and there are diodes, let me call it D1, D2, D3, D4. This is the input voltage, and we want to see what is the output voltage. The load is still a resistive load. Let me call it V0 prime so that I can draw it on the same waveform, V0 prime. Alright, now how would output voltage look like in this case? Okay, how many of you know how the output voltage look like? Raise your hand so that I know how many of you know. Okay, anyone who didn't raise the hand? Okay, so you know it, very good. The positive, when the input voltage is positive, right? Let's say at this instant T1, your input voltage is positive. That means point alpha is at a higher potential than point beta, right? At T equal to T1, potential at alpha is greater than potential at beta with respect to some, let's say, common earth. Now, which of the diodes will conduct, whether D1 will conduct or D3 will conduct? D1 or D3? There's an input source, right? At T equal to T1, the input voltage is positive slightly, right? Let's say 1 volt, 2 volt, 5 volt, 10 volt, whatever. The question is which of the diodes will conduct? D1 will conduct or D3 will conduct? Where we can see that at T equal to T1, V alpha is more than V beta, right? We don't know about anode to cathode voltages, right? What we know is only V alpha is more than V beta. Now D1 will conduct or D3 will conduct. Okay, how many of you think D1 will conduct? Raise your hand. Okay, how many of you think D3 will conduct? Raise your hand. Okay, last person, why would D1 conduct? Sorry? But you don't know what is, no, say again, it will conduct because, no. In this diode structure, you see on the left side, this part is what we call it anode, this is what we call it as cathode. A diode conducts when the anode potential is more than the cathode. Okay? So let me ask the question again, D1 will conduct, the answer is right, but why will D1 conduct? Anyone else wants to answer it? Go ahead. Why will D1 conduct? So many of you raised hand, D1 will conduct, which is right. Why will D1 conduct? Or can you explain me how would D1 conduct? Go ahead to try. I know D1 and D2 will conduct, yes. No, but my question is why? Okay, let me say, let me assume that D1 will not conduct, D3 will conduct. Can you disprove me? We don't know what is V naught as of now.
We just assume V is the potential. So if V is the potential, then D3 will conduct and D4 will also conduct. And by doing second answer after that, you can disprove.
You have to disprove basically. So let's assume D3 conducts, right? If D3 conducts, V beta is same as V gamma, right? If D3 conducts, V beta is same as V gamma, and therefore potential across anode to cathode for D1, which is nothing but V alpha minus V gamma, is also positive, right? Because V alpha is more than V beta, and therefore D1 will also conduct, right? So if I assume D3 conducts, D1 will conduct. If I assume D1 conducts, then D3 will not conduct. And then sort of you get the sense and you can prove it that D1 will conduct, D3 will not conduct, right? Nothing to do with the output voltage. So this is what configuration we call it as a common cathode configuration, right? This is called as common cathode condition, not condition, configuration. That means if you have two diodes like these, and their cathodes are short circuited, and you have whole lot of other circuits, both sides, don't worry about those circuits, then whichever anode is at a higher potential, only that diode will conduct, the other diode will not conduct, right. So whenever you see this circuit in future, you can easily make out which one will conduct, whoever's anode is more. And how to sort of prove it or how to accept it is, you assume the other is conducting, you can say that this will also conduct, but if this is conducting, the other will not conduct, and hence prove that this would be the only guy conducting. Is that okay? Any doubt? This is common cathode. Similarly, you can see common anode. You look at D2 and D4, which one will conduct at T1? Which one will conduct? D2, because the cathode potential of D2 is less, right. So that forms the common anode configuration, right. Common anode configuration is whichever potential is lower, that diode will conduct, right. Whichever potential is lower, that diode will conduct, the other will not conduct. Okay. Rest I think you know. So you know the operation of the rectifier circuit. There is a resistance connected, so the output voltage will be like this. Any question, any doubt? No doubt? You want me to repeat any part? Okay, then let's make our life a bit more complicated. Instead of only a resistive load, let's just add a little bit of inductor in the load, right. So now the load is R and L load, and let's say we still look at the half wave circuit, right. Is this circuit visible at the back? I am trying to draw it very small, but I just want to, is visible? Oh, so I can write small then. It's visible? Okay. So my output voltage I am referring to is the combination of R and L, right? So think of R and L as your load, right? You have seen the rheostats in the lab, machines lab last semester. Those rheostats, if you see, they are resistance, variable resistance, but they are wound in a coil kind of a fashion, right? And therefore, of course, they would also have inductance. So just imagine a practical rheostat is connected across the output terminal, right? And you are measuring the voltage across the rheostat. In fact, you can do this experiment in the lab also, right? If you want. So now I've connected an input source which is an AC voltage and a diode half wave rectifier or just a single diode, so to say, and a R and a L, right. Now in this case, what would be the output voltage? And now immediately I am starting the circuit. What would be the output voltage at T1? Same as input, right? Because you have a positive voltage at the anode. Initially there was no current. If there is no current, there is no voltage drop across inductor, no voltage drop across resistance, right? I R is equal to 0, L di by dt, current is also 0, 0. So therefore the anode potential is more than the cathode potential and the diode will start conducting. As soon as the diode starts conducting, some current will also of course start flowing. So your output voltage in this case will follow the input voltage, and let me also try to draw the output current now. And the output current will also maybe look, not exactly the same, but it would also rise with the voltage, because if it would have been pure resistance, this would have been exactly the same shape as V naught. Now because there is an inductor, right, the equation of output voltage is I naught into R plus L d I naught by dt. Right. So applied, given if I know the voltage, if there would have been no inductor, the shape of I naught would have been same as V naught. Now because there is an inductor, right, shape of I naught will not be same as V naught, but I naught will also rise. Is that okay? So far is this fine? Output voltage, output current. Now the question is, what happens after T2? T2 is the point at which input voltage hits the peak, right? What happens after T2? What happens after T2? Will your diode still conduct or will it just stop? Will your diode still conduct or will it just stop? Will it conduct or will it stop? How many of you say it will stop conducting? How many of you say it will continue conducting? Okay, yeah, so it will continue conducting. There are two reasons, of course. One reason is the way we have seen before, right? If you have a resistance, it will of course conduct for half wave, right? There is no question about it. But now there is an additional factor which is the inductor, right? And as we understand that inductor current you cannot break. This is that means inductor needs a path for the current to flow through, right? So it will flow through the diode. There is no question about it, right? So your output voltage will continue to follow the input voltage. The diode will continue to conduct till the half cycle at least, and we'll see what happens after the half cycle. But till the half cycle, your diode will continue to conduct. What will happen to the current after T2 till T3? Will the current continue to rise or will it fall? What will happen to the current? What will happen to the current? Okay. So if you see, if I rewrite this equation, I can say V naught minus I naught into R, sorry. So for current to fall, di by dt should be negative, right? Now at this instant, if you see the output voltage is reducing, current may also be reducing or may not be reducing, because as a large inductor, it will take some time for the current to reduce, right? It will not suddenly reduce. So if you just assume that immediately after T2, the voltage has dropped little bit, right? But the current is more or less, let's say, the same. In that case, V naught minus I naught R will be negative and your current will start reducing. Is that okay? How fast it reduces depends on the inductor. If you don't have inductor, then you know it's a resistance, so current will just be in the same shape, right? In this case, it will not be the same shape. It will reduce, but not as fast as if you don't have any resistance, right? So if I draw with the dotted line, what would have happened if you had a resistance? In this case, you will not drop very as fast, but you will still drop, right? So let's say you are still dropping, but not as fast. Is that okay? You can of course write the equation, you can find an exact expression, there's nobody stopping you, but this way of doing it gives you an intuition which is very important, not now, but later on when you look at more complicated circuits, right? So this is the whole idea of explaining you this way so that you develop intuition in solving these circuits. Any questions so far? Which point? Don't tell me the whole point. Okay. So the equation is fine, V naught minus I naught R is equal to L di naught by dt. So immediately after T2, assuming there is a large inductor, the current remains same. So I naught R remains the same, which was there just at T2, but the voltage has reduced, right? And therefore there is and therefore the slope may become negative, but it will not be as negative as was the case when you had a pure resistance, or the slope will not be as steep, right? Because inductor will try to hold the current basically. In fact, let me correct it, there is a little bit of mistake. When the current was rising, right, again it was not rising with the same speed as it was rising in a resistance case. So let me just redraw this, sorry. Okay, so let's say this was the resistance case. Here while rising it was not able to rise at the same speed, right? Since it didn't reach the top, immediately at t equal to T2, your V naught is still more than I naught into R, right? So maybe it will continue to further rise till some point and then it will start reducing with a smaller slope. So even the peak may not happen at t equal to T2 because there is an R and L, right? R and L together will cause a phase shift, phase lag. So if you have a sinusoidal voltage, if you connect R and L, the peak will get shifted from the peak, right, from the voltage peak. So the peak also may not happen at T2, peak may also happen a little bit later. Why? Because the current was rising slowly. And whenever the peak happens, then the current starts falling again slowly. Is it okay? Confused?
Isn't the current supposed to lag?
Yeah, it's lagging, right?
So then
Therefore, the peak comes a little bit later. Lag means peak comes later, right? That's the lag. So it's lagging.
but should it also start from origin?
Because at t equal to 0, circuit was off, everything was off. Let's say there was a hypothetically a switch here which you closed at t equal to 0 and you started your circuit at t equal to 0, right? In the next cycle, it will not start from origin. Maybe, maybe not, we'll see. But any other question if that helps you clarify? Okay, so it starts from origin, it grows up with a smaller pace as compared to a pure resistance. It hits a peak little bit later than the peak when it would have hit with a pure resistance. Then it starts dropping again with a smaller slope, right? And at t equal to T3, unlike the pure resistance case where the current would have become 0, here the current may not be able to come back to 0, right? Now this is the interesting part. Now tell me what happens at T3 plus. What will be the output voltage at T3 plus? If I had a pure resistance, what would have been the output voltage at T3 plus? 0. What will be the output voltage now at T3 plus? What will be the output voltage now at T3 plus? Take a guess. 0, okay, 0 is one option. Any other? Impulsive, okay, second option impulsive. Any other? So 0, impulsive, Some negative voltage. Okay, that's the third option. Anyone else? Diode will still conduct. Very good. Fourth option. Needs to rise a little bit. Sixth option. Okay, we have so many options now. So, how many of you think diode will still conduct? Yeah, that's the right answer, right? That's the right answer, and I think more or less you would have converged to the same answer. Question is, why will diode conduct? We always learned that if anode is positive with respect to cathode, diode conducts. If anode is not positive with respect to the cathode, diode does not conduct. And this is how we learned the rectifier circuit with resistance. Now I am suddenly saying that because of the inductor, the diode conducts. So I'm not relating it with the voltage now, I'm relating it with the current. I'm saying that, because there's an inductor, there's no other path for the current to flow through, diode will continue to flow the current. So, but diode is the same, right? How did the diode change his or her mind? I mean,
Input voltage is not across the diode, it's across, there's a RLL in the middle.
Correct.
So that across the diode, you can still have a net positive.
But how do you know? Maybe you have positive, maybe you don't have positive, right? How do you know?
Because the inductor will resist the, trying to make it negative.
Okay.
And at T3, LDI by dt, we already assume di naught by dt is negative.
Yeah.
And that's how we converge to d naught is 0.
Okay.
So di naught by dt is 0 is negative, so it will obviously be reducing. So
Okay. Anybody else? I'll try to summarize what you guys are suggesting, but anybody else wants to try to explain why, we were always relating diode operation with voltage, anode, cathode voltage. Now I am giving you a new explanation that because there is no path for the current flow, diode will turn on. Now you should be confused, right? What is this new definition of diode turning on? Yeah. But then diode doesn't know there's an inductor there, right? I mean, diode is diode, inductor is inductor, they don't talk to each other. Yeah, so inductor will act as a voltage source, right? Again, let's try to disprove, right, the way we did in common anode, common cathode configuration. Let's try to apply that. Let's assume that the inductor current suddenly becomes 0. The diode turns off, hypothetically. Okay? Hypothetically assume the diode turns off at t equal to T3, the current suddenly drops from whatever was the value to 0. What will be di by dt? Di by dt will be infinity, and this would be the polarity V equal to L di by dt minus infinity with this polarity, right? That means the top point of the inductor will be at minus infinity will be at minus infinity with respect to the negative point. So the negative point will be at a very large potential with respect to the positive point in this diode, in this inductor. And now with a small voltage source, 20 volt, 30 volt, 100 volt, doesn't really matter to this infinity, right? And you see the anode has become, because of the Kirchhoff's voltage law, at a very high potential with respect to the cathode. So the diode will still conduct, right? So actually it will not become infinity, but it's just a way of, for us to understand that we assume that hypothetically it stops and we realize, oh, it cannot, because the potential will become infinity, right? And this is what in parts I think some of you were also trying to say. So although we would keep now onwards, we will not give this explanation. I would just directly say because there is no path for the current to flow through, diode will still conduct. But that actually translates somehow again to the basic definition of anode potential being greater than cathode potential. Is that okay? Excellent. So then what will be the output voltage? Output voltage will continue to follow the input voltage because diode is still conducting, right? What will happen to the inductor current? Inductor current will continue to fall. The point it becomes 0 is the interesting point. Let's call it T4. What happens after T4 now? What happens after T4? Okay, one option, stops conducting. Other option? Any other option? Okay, how many of you think it will stop conducting? Raise your hand. Okay, some people think that way. Yeah, it would stop conducting because now the inductor current is 0. So in a way, inductor can now peacefully sit there if inductor wants to, right? Diode, of course, had this tendency of getting negative bias because of the input voltage. We are not able to do that because of the inductor current being non-zero. Now, since inductor current has become equal to 0, diode would happily, use the input voltage and then just shut down. So this is how the voltage and the current would look like in this case, if you add a little bit of inductor. Okay. The next cycle, again the story starts. Let's just make it a bit more interesting. This was a small L and R, right? Let's say this is the case with a regular L and R. What happens at T4? The current is 0. So if current is 0, again let's apply the same thing, right? That okay, now whether diode will conduct or not. Hypothetically, let's assume diode will not conduct. So di verity is 0. Current in the resistance is 0 anyways. So I into R is also 0. Input voltage is negative. So the input voltage, if you add the voltage sources, Kirchhoff's voltage law, the voltage across anode to cathode, and if you try to calculate, you will get a negative voltage. So that will turn off. From T3 to T4, yeah, T3 to T4, it's conducting because of the inductor, right? But now you have a negative voltage, and therefore, if you see the Kirchhoff's voltage law, V0 is equal to I naught R plus L di verity, your di verity will be negative. It will continue to fall. So the current is still falling with some slope depending on R and L, and yeah, till T4 comes. No, it won't be. That's what I'm saying. Please don't quote me that way. That's not what I mean. That's not what I mean. I'm saying we can imagine that if diode turns off, it actually never becomes minus infinity because the diode never turns off that way, right? Yeah. Mm-hmm. Ignore the diode means? You cannot ignore the diode. The diode is the most important person in this room. How can you ignore the diode? Huh? Yeah.
Since without diode it is a linear circuit, frequency of the current should be the same as the frequency of the voltage. So how is the time period for the first half cycle different from that of the voltage?
Very good question. Very good question. Wait, you want to answer his question? Huh? You want to try answering his question? Is that, or you have some other question?
Sir, actually, what the thing is, I feel like in the initial situation, mostly doesn't happen with the voltage.
Okay, no. 1 second. So let me repeat his question first. So his question is that your diode is conducting from 0 to T4, right? And in this period, diode is ideal diode we have considered, so it's like a short circuit. So in that period, your circuit is a linear circuit, right? And in that case, we have learned in the previous course, and good you remember it, that if you have a frequency of F1 in your linear circuit, then all the currents and voltages would be of the same frequency F1, right? So if your source is 50 Hertz, which is this period in which it goes 0, but then the frequency of I0 does not seem to be the same. That's his question. Okay. Now, if somebody wants to answer it, go ahead.
Because every time here we're starting from a completely 0 point. So the situation of every frequency should be the same happen in the steady state. So over like a few seconds, depending on the frequency we have, it stabilizes to 50 Hertz, 60 Hertz, whatever. But here, if the diode wasn't there, IO would have continued to go negative, but it wouldn't have become 0 again in time when P in would start its next cycle. So it would have been a proper phase shift, and over 1-2 cycles you would see that the frequency has become the same. But because of the diode, it's starting fresh every time.
Okay. You understood what he said? You are convinced? Sort of. Okay. Anyone else wants to add?
So this is a transient state and it takes time. That analysis was for sinusoidal states.
Yeah. So two things, I think maybe both of you are trying to say the same thing. One is that look, it's a non-linear circuit. It's not a linear circuit, right? There's a diode, it's not a linear circuit. Now what you are saying is, sir, okay, forget about the whole period, I'll only look at this small period. It's a linear circuit, yes, but then in this small period you don't have sinusoidal steady state. You have only one, you are not able to complete a cycle. It's a half of a cycle, right? So you cannot use the same explanation here. In fact, if I end up redrawing it, right, if I end up drawing it for multiple cycles, you would see that of course I naught is repeating at the same frequency as that of V in, right. If I draw multiple cycles, you will see that I naught or V naught for that matter is repeating at the same rate as V in, right. But then it does not have the same frequency, because if you do the frequency transformation of I naught, right, you go back and you can try doing it, and I will also tell you how to do it. You will find 50 hertz plus you will find other frequencies also, right. So it's a non-linear circuit. So if you are exciting with 50 hertz, there is no guarantee you will only get, in fact there is guarantee that you will get other components as well, right, more than 50 hertz. Alright. I want you to sort of, again physically tell me how would things change if I make the inductor value very, very large. Very large.
It has more power to sustain the current for longer.
Yeah, but takes more power to increase the current. So L is very, very large. You are right. L is very, very large.
I not practically remains.
We can counteract the diverse effect for longer to continue sustaining it.
Okay, let me ask you one more concrete question. If I don't have a resistance, I have only an inductor, right? What will be the output voltage? So do it with your pen, paper, copy. Do it. All of you should do it. Even if you don't, if you know the answer, don't guess. Don't tell me now. Spend few minutes, 2-3 minutes. There is no resistance. There is only an inductor. What will be the output voltage? Once you have drawn it, then maybe we can ask everyone. But first, let's say everyone draws the output voltage waveform and the output current waveforms for this large L, right? And whenever you are drawing these waveforms, right, in this course, you will be drawing a lot of waveforms. Make sure they are time aligned, right? They are different axes, but the times are same. And if at all, it helps you. In my page, there are these grid lines. In your answer sheets, you will not have grid lines. So you can, just to make sure approximately you are drawing the same, you can, draw some vertical lines like these, which will help you sort of clearly indicate what you are trying to say, right. So this is something which you can use if you don't have these grid lines, so that your time synchronize all the waveforms. Don't sort of search it and try to find the answer, huh? Just try it out. Okay, so let's hear from you now. What do you think is the answer? Bhai.
The same as E naught would be approximately same as V and I would be.
Okay.
It will perfectly follow the input and the current will always be positive.
Okay. Yeah. Yes. There's only an inductor. A sharp fall in what? Voltage? Okay. Anyone else? So we have two answers. So I'll tell you, how to do it is there's no shortcut, right? There's no shortcut. You cannot figure it out quickly. The only way is that you have to do the same way, the same hard way we did the left circuit. Start drawing. At every point you try to think what will happen. Every point you keep drawing. Every point you keep thinking. Every point you keep drawing. Every point you keep thinking. You will get the right answer. Don't try to guess the answer. Don't try to generalize the answer. It will not happen. It will make your So you start from t equal to 0. Think what will happen at t equal to 0 plus positive voltage. Current is 0. So the output voltage will also become positive. If the output voltage becomes positive, current di by dt is also positive, current will rise. There is no resistance now, so the equation is V naught is equal to L di by dt. Then the voltage becomes, continues to grow, the current will also continue to grow, right? The voltage starts reducing now, so instead of the top voltage of 50 volt, now it has become 48 volt. Still voltage is positive, so V naught is equal to L di by dt is still positive. Oops, so the current will still continue to grow, right? Even though the voltage is reducing, current will continue to grow because di by dt is positive. When voltage becomes 0, that is the point when di by dt becomes 0, so you hit the top. There is inductor current, you cannot suddenly stop the diode now, we have seen the reason for that. So the output voltage will continue to fall, the current will continue to fall. Current will continue to fall now because output voltage is negative, di by dt is negative. And the question is, when will this output current become equal to 0? Maybe if it becomes equal to 0 here, then it will conduct like this point and then it will stop, and this might be your output voltage, right? Is that okay? Is that okay? How many of you think this is okay?
Well, on solving the differential equation, the current has the same frequency as the input.
But then you just try to argue, maybe you are correct, but any other argument? What I am saying is, current when goes up, when voltage is positive, when you are coming back, voltage is negative, current is falling. Maybe current will fall to 0 at some point, and that is where your voltage will become 0, and this would be your output voltage. Why would it be symmetric? उसको तो मालूम नहीं है ना कि symmetric रहना है. Why would it be symmetric? Yeah?
Because since PO is following B
Mm-hmm.
and PO is equal to LDI by dt, the slope the slope of the di by dt will actually be the same while rising and just the negative of it while falling.
Mm-hmm.
So from 0 to the halfway point, the amount it rises, it would need that much time only to fall again. So then it should end at the exact point where the
Okay. So, are you guys convinced that this situation will not happen? Are you guys convinced that this situation will not happen? Are all of you convinced this situation will not happen? What will actually happen is, the current will become 0 exactly at 2 pi period, where the full cycle sort of ends. Exactly at the end, the current will become equal to 0. Why is that so? You take this differential equation, R is 0, so you have V naught is equal to L di naught by dt, right? Where if diode is conducting, V naught is equal to V in. You take the dt integral there, you integrate V naught into dt from 0 to, let's say, t4 or whatever, t1 is equal to L integral of di naught, and the current goes from 0 to 0, right? So t1 is the instant when current will again become equal to 0, right? Now what it means is the integral of V naught dt must be equal to 0 for current to become 0, right? So what is the integral? Integral is nothing but the area under this curve, right? So when will the total area become equal to 0? At this point, no, the positive is much bigger than the negative. Only at this point, when the positive and the negative area under the curve matches, then this term will become 0 and you will have current again equal to 0, right? So your current 0 will happen exactly at that instant, and then life will keep on repeating as it is. If you have pure inductor, of course in reality you can never have pure inductor. In simulation you can try, but in reality you will never have pure inductor, right? Even in simulation also you would most likely have device resistances and so on, But if you had a pure inductor, this is how it would have looked like. Okay, any question?
Actually, at 0 and 2 pi, the slope of the current is 0. It's the minima point of a upward shifted sinusoid.
I'm afraid
If you solve the differential equation,
it does come out to be like that.
V0
Maybe.
by L into 1 minus cos omega.
Yeah, you are correct. You are correct. You are correct.
That's why it has the same frequency also as the.
Yes, now it's practically a linear circuit, diode is always on, right? So it's the same circuit. Okay, any other doubt? Is it clear? Then assignment question number 2. Do both the things for a full bridge rectifier. You are not doing it now, do it for a full bridge rectifier. We did for half wave, just one diode. Now you have 4 diodes. In the load, case 1, consider a practical L plus R. Case 2, of course, you can consider a pure R as case 1, which you know the answer. Case 2, an R plus L. Case 3, a pure L, right? And see what happens. Have you seen this circuit before? Have you seen a rectifier with a capacitor at the output before? Sure? Where? First year course? Okay. Even in analog? Okay, good. Fine, good if you have seen this. We'll have a look at it maybe in the next class. Time is not there, right? So we'll continue it from next week then on this one.